Okay, thanks everyone for coming to this. We have a talk today by Franziskus Kiefer. Franziskus is affiliated with a load of cryptographic verification work over the years, including the hacspec project, which is a fully featured crypto library with verification built in. So today, Franziskus is going to talk about, it's something that might sound, it's an executable language for specifying cryptography. Now, that might sound like something we're all very familiar with, but in this case, we're talking about hacspec rather than cryptol. And the difference is that where cryptol was created by a bunch of Haskell nerds, hacspec was created by a bunch of Rust nerds. Excited about this. I think hacspec is a super exciting project. I think there's a lot that we can learn here, and yeah, I think that's it. Take it away, Franziskus.
Thanks, and thanks for having me. So yeah, I have a number of slides, actually like 45 or something. But I also don't want to ramble on. So if you have any questions, raise your hand or type something in the chat or whatever. Happy to answer them. And so we might give a quick introduction. I also have a quick intro on myself here. So maybe the last point is actually the most important one. I'm not actually a PL person, compared to a lot of you probably. So my background is actually in provable cryptography. So my PhD is in password-based cryptography and like writing handwritten proofs and games and stuff. I moved on from that to actually writing cryptography, so something that you can actually use, not just like have fancy proofs. And so, yeah, after maintaining NSS for Mozilla for a couple of years and working on like encrypted messaging, last year I started my own company with 2 co-founders, and we're doing sort of similar things to what you are all doing, which is high assurance software, what we call it, mostly in the crypto space, not the blockchain crypto space, but the actual crypto space. We have this awesome website. I hope at some point we actually redesign it and have proper content on there. But so far, Mike already mentioned hacspec, and some of the big projects we're currently working on are mostly around hacspec and actually getting it into a shape where it's usable by someone who does not know fstar and doesn't want to install like the fstar toolchain. You might know one of my co-founders, or maybe both of them. Kartik Bhargavan is probably relatively well known if you know PL, and one of the authors behind fstar and the Everest project. And Jonathan Prosenko is with Microsoft Research, and he is also involved with like the hacspec project. So that's our founding team. We have like 1 additional engineer here we just hired, and we hopefully add like 2 more people to the team later this year. But I want to talk about hacspec, right? Not about Crispin. So before actually going into any of the juicy details of what the language is, I want to give a little bit of history, where we are coming from. And Mike said we are all into Rust. That's true, but that hasn't always been the case. So actually, hacspec originated at the Hex Workshop 2018. This is a picture of the flip chart where we tried to come up with something. And you already see like 3 pretty big bullet points that are important, which is like succinct, well, syntax trackable, obviously, and testable. And so this is where all of this started. The Hex Workshop, in case you don't know it, ask Mike about it. It's an awesome workshop around high assurance crypto software. And so we ended up writing a relatively short paper about it, published at SSR 2018. Back then I was still with Mozilla, and the goals were the same as they are right now, which is like a succinct, easy to read specification language that lends itself to formal verification. So this may be already the first difference if you think about like cryptol and hacspec. Hacspec itself doesn't actually do any sort of formal verification, and it's specifically not designed to be a new verification framework because we have enough, right? So there are so many frameworks and tools out there. That's not what we are after. What we were after is really a front-end language that people can use. But I'll talk about that later. So the original version of hacspec was Python, and this is how it looked. Looks like Python code, right? You have this type-checked annotation up there to actually type-check it, and it sort of worked. It was okay-ish. We had a paper on it, right? And so DJB used it in the Gimli specification for the lightweight crypto competition by NIST. So they actually wrote a hacspec implementation of Gimli, which is nice, and it worked. I'm not sure if it had any impact on the actual standardization process, but that's exactly sort of the use case we were thinking about. I'll get to that later. But Python isn't really the best language to try to do like not verification in, but as a starting point for verification, because Python is way too flexible. You can do anything, right? I mean, you probably, I don't know if you write Python daily, but I'm sure you know what you can do, and it is way too much if you then want to like rigorously reason about it later on. Then there wasn't all that much interest in the version we did. We got like some contributions, we got some users like DJB, but yeah, there wasn't really, people didn't think it was cool. Another issue, of course, it's super slow because, well, it's Python, so it's not fast. And we had a pretty complex tool chain. So you needed like OCaml and stuff to actually do something with it. And so it was better than trying to use F*, but still too hard for people to actually use. It's still online. I have the URL on here, and you get the slides later, I guess, and you can have a look at it. But that's archived and not what we are working on right now. So that was a fail. But well, we still thought we need a language like this. So we still had this idea of having like this usable front-end language for verification. And so just before COVID hit, we decided, okay, let's redo this in Rust. Even before we did the Python version, we actually thought about doing this in Rust, but we had doubts that it might be too complicated and like people wouldn't know how to write Rust, and it was supposed to be usable, right? And so the idea has always been there, but then we said, okay, let's retry it, and especially for our use cases, which is mostly like cryptography related, everyone is using Rust. Well, most people are using Rust, and it's like the hot new language for cryptography. And then, of course, compared to Python, Rust lends itself towards formal verification from the beginning because it has way more information that we like all the types and like the borrow checker, like the ownership model, and all these things actually help a lot. Even if we don't do the verification within Rust, it allows us to abstract a lot of the difficulties away. Another one is the community. So the language is supposed to be usable, so we need a lot of people actually using it and need to validate it. And the Rust community in general is great, I think, and likes formal methods and is nice to interact with. And actually, we have a nice use case for that. One example here, where the Rust compiler broke the hacspec type checker, and after we complained about it, they were actually nice enough to come back to us and say, hey, yeah, we can keep this function, because they were deleting this function and it was the only way to actually do what we wanted to do. And so they kept it in, and this is still part of the Rust compiler. So this was one of the ideas why we said, okay, let's do Rust. So I already talked about briefly design goals, and so this is actually one where I would be interested in either now or after the talk, in like what your design goals behind Cryptol were, or if anyone knows. But design goals behind hacspec really are, the first one is one of the most important one. It has to be easy to write for anyone, really. So if it's a cryptographer who is more used to MATLAB or Sage or whatever, or if it's an engineer who's used to C, but we don't consider formal methods people here. So we don't consider someone who is familiar with Haskell. If they are, that's nice, but we want everyone to be able to write this. Because this is the only way to ensure that specs are actually written by people who understand the underlying issues, the underlying algorithms. Otherwise, you have people who know the language, but don't really know the algorithms writing the specs, and that's not always ideal. Another goal was we wanted to have something that's executable and that's easy to switch out. So you can easily switch between like a specification, which is sort of like it's executable and it's something that you might want to test with, or it's just a prototype, and then you can later just easily swap in your production implementation and it just works. So it has to be like in a setting where, well, something like Cryptol, sure, you could probably use it, but it's kind of hard to integrate into like a C project or in a Rust project or C++. Next point with tooling, I think tooling as an engineer, I mean, I consider myself mostly like a crypto engineer. Tooling is one of the most important ones, because if it's kind of difficult to work with, people won't use it. So tooling has to be good. And that's another reason for Rust, right? The Rust tooling in general is awesome. And familiar tooling, again, like if you already know how to use the tooling and don't have to use, like learn new tooling, it's even better. So what did we want to write with it? Well, mostly crypto primitives. So that's where we all started out. We wanted to do like, as you have seen on that flip chart, I think it was like SHA-256 and curve 25519 that we wanted to implement. So crypto primitives is something that we want to be able to write with hacspec. But we want to do more because, especially if you look at the landscape right now, where people are interested in formal verification, it's not necessarily crypto primitives. We know how to do it essentially, but a lot is about like low-level security critical code, like firmware, like secure enclaves, and these sort of things. So that's also something that we wanted to be able to write in hacspec. And then on the next level, and I think that's something where, well, some people consider it important, others don't. I think it's very important, is verifying cryptographic protocols, which so far I think is still relatively academic, but that's something we would like to push more towards actual industry and production grade tooling. So we also want to be able to write crypto protocols in it. And essentially, you can sum it all up as something like we want to be able to write something that looks like an RFC pseudocode. And what we didn't want to do, I just made it on another slide because that's a confusion we get a lot. We did not want to do a new verification tool. It's only a language that's being compiled to languages that then have verification tools. So of course, we had some assumptions around this before we started out. One is, well, first, we can actually write the type of code that we want to write. Like cryptographic code is in general friendly to this type of domain-specific languages as hacspec is. And then because we also want to write protocols, but protocols, the security properties or the proofs that we actually do are very different, right? For cryptographic primitives, you usually have some kind of equivalence proofs between like your optimized implementation and your specification. But for protocols, we actually think you don't need efficient code, but you can just use your specification and just do your security proofs on these specifications. And so because it's not performance critical, you can just run your specification, which is great. We're still working on validating that assumption, but so far it looks good. The next assumption is we actually still need this language. So that's, of course, one of the crucial questions. Do we actually need a language like hacspec? Or do we need a language like cryptol? We think we still do, because RFCs are still just a blob of text with some pseudocode in it, and that's not good. So we still think we very much need specification language that's easy to use. And we also think people still want it, because people, like, right after we started working on the Rust version, people actually got excited again about it, because it was not Python anymore, and it still had the same goals as the previous version, but now in a new and cool language. And the other one is the Rust community actually cares about these sort of things, and we actually had quite a number of good interactions with like the wider Rust community, and they actually like languages like these, like they like DSLs embedded in Rust. So how does the ecosystem look like? What do we have right now? So we obviously have a GitHub repository where it's all in. Essentially, hacspec is two different things and some examples. So we have the standard library, because hacspec itself doesn't use a lot of the native Rust types to make it easier for translation. There are also a lot of other things in there, like secret integers to annotate that you are not allowed to compare integers, for example, because they are secret. So the standard library you don't have to use, but you probably want to use to actually write hacspec, because it makes things so much easier. Then we, of course, have the language folder. The language folder is the type checker, including backends. So right now we have a coq backend, we have a f-star backend, and an easycrypt backend, and they're all in there. And I hope we get more. And then, of course, we have a set of examples where we exercise all the features, and essentially the idea of, like, we want to be able to write crypto primitives, and we want to be able to write like operating system style code. And so to give an overview on the different parties involved right now, we have on the f-star side, it's Kartik, of course, with his working group at INRIA in Paris. And there, like, one of the main use cases is to actually replace all the specifications in hacspec that are currently written in f-star with hacspec specifications. And on the other hand, we are working on protocols. So we are working on a TLS 1.3 implementation, and we have code for things like more protocol-like code, like HPKE, for example. We'll look at that later. On the coq side of things, Bas Pitters in Aarhus is doing a ton of work around hacspec. He has a PhD student doing a lot of work on the type checker right now. He's actually using it a lot for his courses. So he has just some bachelor theses coming in and things where people write hacspec. We'll look at that later as well. But they also integrated hacspec with SS-proof. SS-proof is, in case you're not familiar, is like a relatively new way of doing modular security proofs, similar to like the universal composability model, but nicer and smaller and more understandable. They also added Crusoe integration that you might know. So there's integration for the Perlite annotation language from Crusoe that you can use then in hacspec that's being translated to the coq backend. And they did a lot about testing, because, well, formal verification is great, but you still need to test a lot. So they did a lot of like property-based testing with quick test. And then the third group of people who are involved with hacspec is the easycrypt and Jasmine folks. That's Manuel from Porto, Francois from Bristol, and then Pierre-Yves, who's at Meta by now. And they're looking for like a common specification language for easycrypt and Jasmine. And that's, of course, another nice thing that we were looking for with hacspec, that right now you have all these proofs for either like correctness of code or security properties or whatever, but they are not connected whatsoever usually. But if we have like one specification in front that we then compile to like different backends, we can actually connect all of these proofs through the hacspec specification, which would be nice because it would actually give us like nicer results in the end. In terms of code, so this is actually somewhat outdated in what's on there, but well, we have the usual crypto primitives, but we also have things like the Riot bootloader. Riot is like an open source researchy IoT operating system, and they're currently rewriting their operating system in Rust, and they want to have some of these assurances. So we are working with them to try to implement some of the low-level code in hacspec, and that's working pretty well so far. So later, if you want to see more code, there will be code on the slides as well. Mike told me there should be code. But if you want to see more code later, we can have a look at some of these examples as well. So let's have a real quick look at the language, how it actually looks like. So hacspec itself, there are two ways to look at it. One is that it's a DSL that's embedded in Rust, and that's the way I prefer speaking about it. The other one would be that it's a subset of Rust, which it sort of is, but we are not interested in modeling Rust, right? We are just using the Rust compiler and all the tooling around it to actually define our DSL. We are not actually verifying or translating a subset of Rust in the end. So the language definition itself, actually, I have to warn you, there are a couple of errors in this definition. I just found out by copy pasting it out. This was supposed to be the actual language definition, but it looks like it's outdated. But we have generally the items you would expect from Rust. I just expect you all know some Rust. So we can import modules, we have constants, we have type aliases, and then we have the array exclamation mark, the array macro. This is something that's defined in the standard library, which allows you to use arrays because we don't allow the Rust arrays. This is where you have the difference between being a subset of Rust and actually being a DSL, because we want to have more control over what you can actually do with your arrays, because we want to have clear semantics about the arrays itself. So we don't reuse Rust arrays. Maybe we should, and maybe at some point we will rewrite some of this to actually do, but that's how we started, and that's, I think, what still makes sense for the way the type checker works right now. But we also have like a little more complicated things like field integers or something, which are also defined in the standard library and that are commonly used in crypto specifications. And of course, we have like functions, we have enums, and we have structs. Actually, we don't have structs, we only have tuple structs. So that's actually wrong. Otherwise, path, we do a lot of restrictions on what you can use of Rust. So like a path, we only allow you to import everything because we don't want to parse everything. So this is mostly, well, probably laziness in terms of what we are implementing in the type checker and how we implement the type checker. But we essentially just say, okay, you have to import an entire module. We don't care about you just importing like a couple separate functions. In terms of like we have all the primitive types that you have in Rust, the integer types, the uppercase integers, like the uppercase I and the uppercase U, are for secret integers. So you can use them just as regular integers, but you can't, for example, you can't compare them or you can't divide them, and you have to actively declassify them if you want to do something with them. And then we have sequences, which are essentially Rust vectors underneath, but again, modeled differently because we are in a DSL, not in Rust. Then we have, so in terms of statements, we have inner mutability in functions. We don't allow mutable arguments, but we have inner mutability. And then we have the usual statement that you would expect. We don't have like if expressions or for expressions or like any of the fancier Rust things. But otherwise you can like write most things with this. And in terms of expressions, we also have what you would expect. We have all the variables, function calls, probably for like people coming from C, ranges might be a little new, but we try to keep these like non-standard notations to a minimum. And so I think the language itself, I think we have one more. Yes, so we have operators, right? The language itself is very, very simple and very easy to understand and learn. If you are a Rust programmer, it's probably actually harder to learn hacspec because you want to do like a lot of things that you can't actually do in hacspec. So I usually tend to say people should write C code in Rust, and that's kind of what you can do with hacspec. So how does the type checker work, or how does the language work? So this is, they also took a different path than most other Rust tools that I know of. So most tooling, if it's Cresor or whatever, or even I think Croxmere, usually uses mir as like an abstraction layer and parse, which is nice because you have like, in the end, you have all the information there that you want. But again, hacspec had a very different outset. So we wanted to have readable specifications. And question is, because hacspec itself is not a verification tool, we always first need to translate them into into like a different formal language. And what we wanted to keep is the code structure in the end. So that's the first 2 bullet points here, essentially. We wanted to keep the general control flow and the general way the code looks between the hacspec, the front-end language, and the backend, so F* or coq or whatever you use in the backend. And so that's why we decided to actually operate mostly on the AST, which has sort of like a nice side effect of that you could do this in stable Rust compared to mir, or if you're going to here, you have to use nightly. But then actually hacspec by now also requires some here to get information about external crates and stuff. And so, well, we also have to use nightly and struggle probably with the same issues you're struggling with Croxmere and your tooling to keep up with changes in nightly and things are breaking. So, but this is definitely something where I would also be super interested in hear your take on like where to plug into these compilers and these type of tools. So a quick overview on, yeah, go ahead.
Can I ask a question? Sorry. So it sounds like you basically have no pointers other than arrays and certainly no borrow checking, right? And so does that I guess that means that you have to copy if you're going to, you know, have something that needs to duplicate an array or temporarily duplicate an array or something like that. And so my question is, does that basically just not come up in crypto code? Or is that an issue that people have to kind of think about and work around if they're trying to make performant code?
Yeah, so yeah, very good point. So first, well, we can borrow, right? So we can borrow, but we can't borrow mutably. So if it's just about getting the information into a function, you can just pass in the pointer, right? So that's okay. But if you want to return something, you would have to copy it and like return a copy. So that you think might be an issue, but actually if you consider, well, if you only write essentially functional code in Rust, and that way essentially just pass in the variable and return whatever modified version you have, the compiler is pretty good in optimizing this. So we did some performance tests with this, and you get reasonably fast code this way, at least for protocols, for example. For crypto primitives, usually you need to do like a lot more fancy stuff anyway. So like efficient crypto code would probably need a little more support, let's say, from the language. But protocol code, where it's just about like state passing, for example, or something, these copies are actually not an issue, I think.
Interesting. So maybe it would be a little hard to write AES or something, though. I mean, thinking about that more, I guess that would probably fit nicely into this model anyway, right? Okay. Yes, that makes sense. All right. And I guess the shared borrows for would alleviate a lot of the potential issues, right? Because you can still pass around read-only slices of arrays, basically.
Yes.
Okay, thanks.
Sure. Yeah, so performance in general, I think is an interesting question. And I would actually be interested in having, so you mentioned AES, right? And to implement AES safely and efficiently, you need hardware support anyway. So for me, an interesting idea would be to have sort of hardware abstraction within hacspec. So you can call into AES instructions or into SIMD instructions or something, and just assume they are safe and they are correct. And if you then could write actually efficient crypto primitives in hacspec, that's an interesting question, I think. So back to the type checker. I already said like we are mostly operating on the AST. This is not up to date anymore because we are using some here information by now. But in general, we have the Rust AST. We generate like the hacspec AST, which is type checked, and that we use to generate then fstar or camel or whatever other code you would like, depending on what backends are available. So what can you actually do with hacspec right now? So you can obviously write specifications. You can, well, we have these backends, so you can translate the code. That's all more or less working. So the backends are all not on like the same level. For example, we didn't have anyone working on the fstar backend for a while. We have someone new starting on it like this week or last week. So the level of these backends differ a lot. But in general, you can write code and extract it to most of the backends. And then, of course, you can do whatever sort of proofs you want to do there. How easy these proofs are and like how many like manual changes you have to do to the translated code is a different question. But we actually have, well, we have some tooling for this. So, for example, we allow you to, if you have, for example, if you added annotations to the extracted cop code, you can recompile hacspec to coq with like small changes, and it will just do the diff and re-add your annotations. So you actually have like a nicer workflow than like every time having to copy your changes again into like the newly generated code. It's not perfect, but for like a lot like smaller changes, it works. Like other use cases for hacspec are generating test vectors. So we just like one of us students did the RSA PSS VRF, which is currently being standardized by the CFRG. And there haven't been any test vectors, so they contributed test vectors that came out of hacspec. That's nice. So that's also a good use case. Test target, I think, is in general like a very important use case, because usually first thing you want to do when you have like some new code and some new optimized code, you want to test against something, and having a nice and clean hacspec is a good test target. And of course, you can just use it for prototyping new stuff where you don't really care about like performance in the beginning and want to just have something that you might want to use later on for verification or test targets. So now we can actually look at code. So you might know what this is, or you might not know. This is a Poly 1305, at least most of it, without some unnecessary definitions. But I mostly put this on here so you see that it essentially looks, well, it's kind of readable. It somewhat looks like Rust, because it is Rust, of course, but it also has some differences. So like you have the uppercase U128, for example, in line 97, which is just making this like a secret integer. And then you have these, like you have field elements, where like in line, oh, the one is missing there. So in line 105, we add the 2 elements. And so because it's a field element, and that's part of the hacspec standard library, we don't have to do like any modulo and anything that's like implicit in the addition here. And to compare it to like one of the goals we had, which is like we want to write RFC like pseudocode, we can look how the actual poly function. So this is the core poly function from RFC 8439. So I know you also have a cryptol version of this, so that's why I took this and thought maybe some of you are familiar with it, even though it's pretty old by now. So this is how the RFC code looks, and I think this is sort of like the type of code people understand and people like to see in RFCs. And here we have the hacspec version of it, which it doesn't look very rusty if you first look at it, because there are things that well, this for loop is probably something you would not do in Rust. But again, that's where I said this looks more like C probably. But if you put these two next to each other, I think, at least in my opinion, let me know if you disagree. The hacspec version looks pretty close to the RFC version, and except for these chunks, for example, the way the chunking works. And so this was one of the main goals, to make sure we have like a language that we could put into an RFC. We don't want to yet, because it's not stable by any means. But at some point, we want to get there that you could actually put something like the hacspec code on the left side into an RFC, and that way actually have like an executable pseudocode in RFC. And we also have a cryptol version, right? So I think there are 2 different versions of Poly, at least publicly, that I found. And we actually use this in NSS as well to prove correctness of the NSS implementation of Poly and Chacha. But at least to my eyes, I mean, I can read the code in here, but I don't think anyone at CFRG or IETF would be happy with pseudocode like this. And then, of course, another thing is it abstracts a lot already on the actual RFC. So like the first 2 sentences already show an issue in the RFC. So it says we actually divide into 16-byte blocks, and the last block might be shorter. But then if you look at the actual RFC, that's not what the RFC does. And that has been one of the errata. And that's also like one of the things that we think, or why we think it's so important to have an executable specification language, because if people would have actually used this pseudocode, they would have noticed it's not working in some cases and would have done something about it. But because it's just some blob of text, probably no one noticed until it was too late and it was published already. So that's like one of the things we like to kind of point out when talking about hacspec, is that like these sort of issues hopefully shouldn't happen if you use something like hacspec. Now I want to show something slightly different. It's also not directly code, but there is code in there, and goes back to the awesome tooling that we have. And that's something we call annotated specifications. I have to switch my screen share. I hope this works. So you should see my browser. So what we would like to have something like hacspec in an RFC, but we also like the other way around. So because we have so nice tooling in Rust and we don't really have to do anything for it, we can have something that we call annotated specifications. So this is essentially the entire RFC within hacspec. So this is an executable specification where, so in case you don't know what HPKE is an RFC for hybrid public key encryption, which essentially standardizes. The easiest way to explain it usually is it standardizes the way something like PGP works, where you encrypt for a public key, but you can encrypt arbitrary sizes by using like hybrid encryption. And so we have an executable specification, which is nice. So it allows you actually to look into the different things. So for example, HPKE is using key encapsulation mechanisms. So you can look into how CAMs work, and you can look into, for example, how the encapsulation works. So you have the pseudocode, what's in the RFC, but at the same time, you can of course look at the hacspec code. And here we have the way this looks in hacspec, which I think looks close enough to an RFC that at some point we might actually be able to get something like this in there. And it allows users who just want to implement HPKE, for example, to have something a little more than just an RFC, but something to actually go through, look at the actual code, run the actual code, look at the text, and so have a little more than the textual specification. So that's something we can do with hacspec because it's in Rust. Another nice thing I like to show is, because it's executable, it's also executable in a browser because it's Rust. So we can compile to WASM, and it's not super efficient, but for like this type of demo, it's enough. And so you can actually use HPKE in here. You can open it again, or you can, if you actually change the ciphertext, it will tell you can't decrypt it anymore. But so I think it's way more than just a specification for formal verification, which is, of course, formal verification is what we want to do, but you also have to not only get people to write it and understand it, but also get people to actually see the additional benefits they get with it. And I think this is another nice one. So that's also something you can do. Get back to the presentation. So I also have the links on here. This is all online, so you can actually run it yourself if you want to. This I've just shown. So of course, like these are all just ideas, and we hope it works. But I think we had a couple of nice things recently that showed that at least the usability aspect of hacspec, which was like one of the main reasons we did it, sort of worked out. So this is from some Blockstream folks. So I have very strong opinions on Bitcoin, and they are not in favor of Bitcoin, but they still have some great engineers. And so one of them has been at Hex, and he was interested in hacspec and wanted to see like if he can use it. And so he actually used hacspec to implement these half aggregated signatures in hacspec pretty much on his own. He got some reviews, but really it wasn't wasn't like we did a lot. So it looks like someone who knows like the protocol behind it and is in general like a good engineer, let's say, can write hacspec on their own, which is great and was one of the goals. Similarly, as I said, like BUS students are working a lot with hacspec, and so some of them are just finishing their bachelor thesis, and they used hacspec to implement bulletproofs. So they are also online if you're interested in them. So because we also want to have some time for questions, so I'm almost done with talking, and then we can also look at more code if you want to see more code. So how can you contribute to hacspec if you want to like help making hacspec better? One, of course, is writing new backends. So like I would love to see it like hacspec work with Crooksmere and like be integrated with all your tooling because I really like it. Then of course you should do proofs with the actual translation so that we kind of know how good the translation is, because that's of course you have to fine tune the extraction and over time, and then hopefully like right now for the Coq backend it's sort of okay-ish. For the F-star backend it's not good at all. But yeah, that's something we have to tweak, but we can only tweak when people actually use it to do proofs.
A question.
Yes.
Have you guys considered hacspec itself as a backend for translation? We're thinking about, oh, what if we wanted to generate hacspec from Cryptol as a way to compile our Cryptol into Rust?
I mean, we didn't consider that yet, not from that end at least. So we considered it sort of from the other end because we have all the F-star specs, right? So similarly, from F-star, we might want to like translate them into hacspec automatically. We didn't yet, but it's an interesting question. Is that something you're considering?
Yeah, we're thinking about it. Yeah, I was just trying to, we're trying to kind of think about, because I mean, you have all this tooling and, you have some, a nice fragment of Rust that's going to be efficient, but also kind of cover all of the stuff we might want to be able to do. And so I was just wondering if, if your immediate reaction was, oh, that's a terrible idea for some reason I hadn't thought of, or, I don't know. So the fact that you're talking about compiling F-star, translating F-star into hacspec, I think suggests that maybe that is a good idea. Maybe you are kind of thinking a little bit maybe of hacspec as a potential target and not just as a source.
Yeah, I think so. I think in future, it probably should mostly be the source, but we are in this transition period, right? So we have a lot of code in F-star, like you have a lot of code in Cryptol, and the question is like, how does the future toolchain look like, and what do you want to use in future, and how do we get there? Do you have to rewrite everything you have, or can you translate it? So, and for us, it's kind of thinking about like, how do we get to this new thing that we would like to use without having to redo a lot of this stuff.
Well, that certainly makes sense. I guess one of the aspects that we're thinking a little bit about of hacspec as a translation target is that it's a lot more readable than, I mean, you were talking about, generating mirror or generating, et cetera. And I think it's certainly an interesting idea to think about how your hacspec versions of crypto specs look sort of similar to our Cryptol versions of them. And it might be really useful. I mean, for us, at least, it might be useful to make that correspondence really close and then generate code in our subset of Rust that's actually readable. And so it's a little, anyway, we're just kind of thinking about it. So just wondering what your thoughts were.
Yeah, I definitely think it's a great idea. And especially if it's about readability, because as I said, I mean, I'm fine with Cryptol, but I think a lot of people are not. And so if you want to show people like how your specs look like, they might be more willing to look at like hack specs. So yeah, I like the idea, I think.
Thanks.
So right, we have been proof. So the other things like it would just be great if people would use hacspec in like designs and specifications, similar to like the example I've just shown from the Bitcoin folks. Because just to validate that it's actually usable and validate that it's like useful for people. We have a pretty active Zulip and GitHub community. So like if you want to contribute or if you want to like do something, just join either of them and just tell us like what you want to do or like where you're struggling or like that it's not working at all, probably. And then of course, like language design itself. So the language it's it's working mostly, but it's still not, it's far from done, right? So like we are currently working, as I said, working on a TLS 1.3 implementation. And there are a number of issues that we have to fix in a type checker in the language first before we can actually use it. And so I imagine like there are other use cases people want to use it for, where it's not like about like we need a completely different language, but where it's about like, okay, maybe we need, like in our case, we need to like match on tuples, which isn't in the language right now or something. And that's certainly something where I think everyone would be happy to discuss and like get more features into the language that people need. So just to recap, do this real quick. So we actually have a couple more minutes for questions. So hacspec is, or we hope it is, a usable, succinct, executable DSL that's embedded in Rust or subset of Rust, depending on how you see it. And at least from like a lot of the recent feedback and things we are seeing, it appears to deliver at least on some of the goals so far. But of course, it's still work in progress. And yeah, we have some backends. We would like to have more and better backends. There's also, of course, it's on the industry side as well, but there's also research happening around it. As I said, like Buzz has a PhD student on it. On the FStar side, we'll soon have a postdoc on it again. So there's also active research happening around it if you want to get into that. And of course, there are like industry applications where I think it's nice, like if people are asking you to design something or like design a new protocol or whatever, you can go and tell, okay, I'm giving you like a hacspec implementation, and they will actually be able to read it and use it, and you can still do like verifications on it or whatever. And for that, I think it's unique so far. So I rambled a little longer than I actually wanted to, but I hope it was still interesting enough. And yeah, let me know if you have any other questions.
Yeah, thanks so much, Franziskus. This was awesome. I think it's really impressive, the sort of stuff that's happening with hacspec. And well, for anyone who doesn't know, we are currently building a hacspec integration for our Crux tool. Patrick, who I think is on the call, is working on that. He's an intern. Does anyone have any questions for Franziskus in the 5 minutes that we have left? Yeah, Ian, go ahead.
Hey, can you hear me?
Yeah,
Yes.
just fine.
Okay. So I think my question, I was reading the paper a little bit before your talk, at least the most recent one that I could find, and it presents some nice, formal type rules, but I couldn't find statements of the kinds of properties that the type system was supposed to enforce. And my guess is that it's more than what Rust enforces. Can you say more about what the type system is doing for me? If the hacspec type checker says, yes, your program is good, what sort of things can I infer from that?
Wow, that's sort of a good question. So right now, in my opinion, the type checker actually, well, it does some things, which is not actually, I think, what it should be doing. So in my opinion, the hacspec type checker should not do additional type checking beyond what the Rust compiler is giving you, because that goes back to the one main point I had earlier, which is I don't think we should have another verification tool with hacspec, because we already have so many, and they're all distinct, and like everyone prefers their own tools and whatever. Like that's not the goal of the language, but really it should be a front end for like all the other languages that we compile to. And so in that sense, there are a couple of additional things I think that are happening in the type checker that might be useful, but mostly really not.
Okay, so it sounds like, well, so I agree with you about the verification angle, but I could imagine it checking things like, well, so this gets into another question I had, but I could imagine it checking things like constant time. Or are you imagining that the constant time guarantees are mostly going to come from the libraries that are provided as part of the standard?
Yes, essentially. So that's sort of what the secret integers are doing, and like where the library should provide some additional guarantees about constant time or secret independent computation as much as you can do on that level. But the type checker should not, well, the Rust type checker should be able to do that as well, right?
Thank you, by the way.
I hope that answers your question, sir. Yeah.
Yeah.
I see we have another question online. Just go ahead. Rishi, we don't hear you if you're speaking.
Okay, can you hear me now?
Can hear you now, yeah.
Okay. Yeah, I think it's a variant of the last question. I'm still confused about the purpose of the type checker. If the Rust type checker, is it because the Rust type checker is not able to do something that you need to do, or I don't get why you have a separate type checker, since it's legal Rust and it should go to the Rust type checker itself, unless you're proving some additional properties of the Rust type checker is not checking.
Yeah, so names are a little convoluted, I think, here. So the quote unquote type checker is supposed to ensure that your Rust you're writing is within the hacspec subset of Rust, or is within the domain specific language hacspec that we define. So that's the first purpose. And the second one really is translating it into essentially an intermediate language that then can be used by essentially backends to translate into whatever backend language you want to have. So it's not an actual type checker in the sense that it's checking anything in addition. It's just making sure that you are in the subset you should be in.
Okay. And a follow-up question I have then. So I think that makes sense. So in some sense, you're checking that you're in the DSL, yes, as opposed to using arbitrary Rust in that. So a similar question I had, as a related question, is you can execute in Rust itself because it's legal Rust and you can compile it into Rust, and you also have these backends. Do you see these all as sort of equal status, or these other backends are mainly meant for verification because those backend targets have tools, mature tools for verification? So what is the relationship between, what is the purpose of the different backends beyond variety?
It's essentially, so the main purpose is that, as I said earlier, we all prefer our own tools, right? So there's the community, there's the F-star community, there's the Crooks community. It's like, people probably won't change the tooling they use. So you kind of have to get them where they are. And that's the main purpose of like having the different backends. Yeah.
But is this to produce production code for them to use in their environment, or they're just using it to verify things?
It is. So originally, it was 100% just verifying things, verifying whatever security properties, equivalence, whatever you want to prove. But actually, so on the Coq side, what they did, you know the fiat crypto things from MIT, from Adam. And so they sort of, I can't recall the exact tool chain, but they compiled hacspec to Coq to Bedrock to then compile back to Rust in the end to get sort of like efficient code back out in the end. So it's not necessarily only for verification. I think that was the original idea, but people appear to use it differently as well. So there might be like a reason to generate some other whatever. If you need C code, you could generate C code if you really wanted to. So yeah, I think originally verification, but by now it could be more.
Okay, thank you.
I'm sorry to interrupt there. So I was just going to say we're actually out of time now. So thank you very much, Franziskus. I hope that we get to collaborate with you in future, and it's very exciting to see this work going on. Thanks a lot.
Yeah, thank you so much for having me.
Thanks. Take care.